Okay, hi everybody. It is time for week 4 at Rasmussen. Here is the summary page. It shows you what we're supposed to learn, which is right here. A suggested pacing as always, and as usual, we recommend that you take a couple days to master the foundational material. Begin working on the labs by midweek. There are 3 of them, I think. Lab 1, Lab 2. I think there's actually only 2 of them this week. Don't worry about the discussion posts. You're encouraged to do so, but I won't be checking them like on Tuesday night like I used to. But please do post to the discussion board. I think it's helpful. We'll have our Wednesday evening live classroom at 7 p.m. as usual. You should really get to the assignment by Friday and the quiz by Saturday or sooner. I get some students that submit very early, and this is also just a suggestion. All right, good. So this is the material we'll be learning. I've summarized it by saying we're looking at matter and gas laws. It's quite a bit of material, and when you check out the next slide, I think you'll see that we've distilled it down to its essence. Here's the actual graded material with its scoring guide. So here's what you need to do in order to earn all 162 points this week. Okay, without further ado, let's have a look. By the way, if you're listening to this pre-recording, I've been getting lots and lots and lots of requests to include the passphrase in these recordings. Now, I kind of hate to do that because attendance is very, very low for the required Wednesday evening classroom. The things I'm hearing from you, from several of you, however, I am, shall we say, sensitive to. Many of you are talking about working long hours as a nurse or in the healthcare field, and believe me, I'm very sensitive to that. So I will include it this week. Please do make an effort to attend the live classroom. It is once a week, and I always reveal the passphrase within the first 15 minutes or so. Okay, let's continue. Now, here's all the topics that are in the foundational material. And if you cover every single one of these deeply, you're going to get really swamped. So what I did was ask myself, should we know it? And I think you should know all these. But another more important question is, should we emphasize it? To answer that, I took a look at the assignment, which covers the material in a certain fashion, as well as the quiz. Now, a lot of these topics are really not covered at all on the assignment, and a few of them are not covered on the quiz. That being the case, we'll make sure we cover everything at least with a very brief coverage, and we'll be emphasizing the topics in red. We'll be covering them in order. The remaining topics we'll be mentioning while we go. So I hope you can see that this should save us a lot of time. The material that we'll be emphasizing is truly the material that you'll be tested on, and I think it's the most important things to know moving forward. Okay, let's begin with states of matter. By the way, you might notice that I'll just cover each one of these red topics in order. So if you want to go fast forward to gas laws, you might want to head down towards the end. States of matter. As you know, everything can exist as a solid, a liquid, or a gas. So let's take any substance and we'll heat it up. If you go cold enough, everything exists in the solid form. Ice, for example, is water in the solid form. Heat it up, and it will turn into a liquid. Heat it further, it will turn into a gas. If you then ionize it, if you run a current through it, you can turn it into a plasma. And plasmas are surprisingly everywhere. Fluorescent lights, for example, do exactly that. They take gases and they run electricity through them and they turn a nice color. Street lights do the same thing. If we go down, let's see. Yes, oh, there is a name for each process. A solid to liquid, what is that process? We call that melting. A liquid to a gas, name that process. I call it boiling. Some people say evaporation. Gas to a plasma. Well, what you have to do to kind of gives you a hint as to what it is, it's ionizing. Let's work our way downhill. You can take a plasma and bring it down into its gaseous form. You just have to deionize it. Turn the current off, if you will. When you turn the current off for a fluorescent light, it turns into a normal, ordinary gas. Cool down that gas and it will turn into a liquid. We call that condensation. We can also turn that liquid into a solid. We call that freezing. And you see these things every day. There's a couple weird ones you don't see every day. You can turn a solid directly into a gas. Only a few substances do that. We call that sublimation. And if it does that, it must also do the opposite. We call that deposition. And deposition is usually the one that people struggle with the most. So those are all the possible phase changes and the phases. If you have something in your hand, it is a form of matter, but is it pure? If it's pure, we call it a substance. If it's not, we call it a mixture. Dirt is a mixture. Water, pure water, would be a substance. It doesn't have to be just an element. Neon is certainly a pure substance, but so is methanol, for example. And if you can't separate it down any further, you could take a pure substance and chop it up into its individual things, but you're going to stop when you hit elements. You can't go any further by chemical process than the elements. Those are the atoms of which everything is composed. So, if you have a substance composed of atoms of two or more elements chemically unified in fixed proportions, we call that a compound or a molecule. My God, what a terrible mixture of words there. I would just call them bonded atoms become compounds or molecules, and let's use those terms interchangeably. I would like to emphasize that the universe as we know it, it's true that it's composed of atoms. I guess you could also say it's composed of protons and neutrons and electrons, but I think it really misses the point. It's more useful to say that the world as we know it is composed of molecules, because those are the substances that have the fixed properties on which everything is based. Water does not have properties remotely similar to hydrogen or oxygen. It's those molecules that I think you really want to focus on. So tell me, is it an element, is it a compound, or is it a mixture? Gold. It is the element Au. The ocean. A mixture of many things. Milk. Homogeneous, but a mixture of many things. Copper. Oh yeah, the element Cu. And glass. You may not know it, but it is a molecule known as silicon dioxide. And if you really get down to it, there's nothing that's 100% pure. It might be 99.999% pure, but really just about everything is a mixture. And we can classify it a little bit further. We can't say much about mixtures if their properties vary, right? One cup of dirt is not the same as another cup of dirt, but at least we can say certain things. We can say whether it's homogeneous or whether it's heterogeneous. If you can only see one thing, we call it homogeneous. If you see it speckled or more than one thing or spotted or crisscrossed, we'll call that heterogeneous. And heterogeneous mixture is just plain old a mixture. There is a special term for a homogeneous mixture. We call that a solution, something that is intimately mixed. And in fact, they don't have to all be like, salt and water. We could come up with a gas-gas solution. Can you think of an example? How about air? We can think of a solid dissolved in a liquid. I always think of salt water. We can actually dissolve gases and liquids, and I drink way too much of some of those. I'm thinking of soda. I don't know if it's going to show up, but soda should be there. Liquids can dissolve in other liquids like gasoline and vinegar, and you can even dissolve another solid, there it is, in another solid, for example, brass and steel and things like that. By the way, PP means that's our passphrase for this week, steel. I hope you caught it. And if you're going to make a solid-solid solution, I would cheat. I'd melt it first, right? I would take some zinc and copper, melt them together, turn them into brass, and then let them cool. And all they do is just intimately mix. They don't react, so it's actually a solid solution. Scientists learned a long time ago that you really can't figure out much about a solution or a heterogeneous mixture for that matter, until you isolate the individual substances. So separation and purification is a huge part of chemistry, as is identification. And things have properties, right? If you have a pure substance, it's going to have all sorts of things, right? You can look them up. Some of them will be chemical in nature. Most of them will be physical in nature. When you talk about the chemical property, you talk about turning it into something else. When you talk about a physical property, you talk about a property where it's not turning into something else. So a chemical property involves, by definition, a chemical reaction. Ask yourself if it's turning into something new. If it is, that's a chemical property. So let's talk about each one of them and think about if it's physical or chemical. I take a substance and I boil it. Is that chemical or physical? It certainly looks like it's forming a new thing, but if you analyzed water in both its liquid and its gaseous form, you'd find out it's exactly the same stuff. Therefore, phase changes are physical. Rusting, like iron to iron oxide, new substance form, it's chemical. Melting, no. Water, ice to liquid water is still water. Rising, well, it's the same thing. It just might be changing in its density, for example. That's a physical property. It's still the same stuff. Burning turns it into something else. That's chemical. Crystallizing sugar to make rock candy. It's still sugar, so it's physical. Flattens something out. That still is the same chunk of gold, for example. That's called a malleability. And if something gets moldy, well, that's some new life form type stuff forming. I'd call that chemical. You can stretch something out if it is ductile, but it's still the same stuff. That's physical. You can, if it is transparent, you can make light bend through it, but you have not changed the substance. It's physical. You can just look at something, and you're certainly not changing it. That is a physical measurement. And if it's shiny, it also does not change it. It's physical. Notice that so many of these are physical properties. It's pretty rare to talk about something in terms of turning it into something else. In other words, chemical properties are less common. Let's learn how to balance chemical reactions, and be warned, both the assignment and the quiz cover this heavily. Here's what we're going to do. You can take sodium and react it with chlorine, and you can turn it into sodium chloride. I just want to see the three numbers in front. That means I'd like to balance it. Mass is always conserved in this world. If you start with 10 grams of something and you do anything to it, you better end up with 10 grams of something else. So if I start with 1 atom of sodium, I better end up with 1 atom of sodium. And it looks like I am. But here I see 2 chlorine atoms there and only 1 there. Therefore, I better put a 2 in front here. I can't make it NaCl2 because that's not sodium chloride. Sodium chloride is +1 -1. However, if I make 2 of these, that makes sense. Start with 2 chlorine atoms, end with 2 chlorine atoms. But wait a minute, what about sodium? I have 2 sodiums, no problem. I'll fix it there. So it's not uncommon to sort of screw it up and then repair it as you go. Here's one that's a little complex. Let's do it together. By the way, you'll get in huge trouble if you try something that appears in more than 2 places until the end. I mean, look at this one. We have oxygen appearing in 3 places. We'll save it for the end. But here, it should be okay. We could start anywhere. I have 1 nitrogen here, but 2 here. We better start with 2. Never change the composition of the substance. That's making it something else. That would be a different chemical reaction. Just change the numbers in front. By drawing these lines, it emphasizes that. So we must start with at least 2 molecules of ammonia. This gives us 6 hydrogens. I like to always use the new information. Imagine 1 NH3, that has 3 hydrogens. Imagine another one, that's what this is. So here I'll draw into air, NH3, NH3, 3, 6 hydrogens. So I better be making at least 3 pairs of hydrogens. So I'm going to put a 3 there. Convince yourself that we have 6 hydrogens here and 6 hydrogens here. You might be saying to yourself, oh, I multiply. And you're right, you do. Are we good? 2 N's, 6 H's, 2 to 1 to 3 looks good to me. All right, here's mastery level. Give this one a try. Do not do oxygen first or you'll be making educated guesses. There would be more than one possible answer. Save it for the end and you will force to get the right answer. Here's butane, C4H10. I got 4 carbons. I better end with 4 carbons. Here's 10 hydrogens. I only have 2. Why don't we make 5 pairs, right? Now, if I put an 8 there, that's something that people think is right. 8 plus 2 makes 10. No, this would be 8 water molecules. That would be 16 hydrogens. But I am balanced with respect to carbon. Check. I'm balanced with respect to hydrogen. Yup. How am I going to do oxygen? Well, here's the trick. I know that I am set for carbon and hydrogen. So if I just count up how many oxygens I made here, I can put a number there. It won't screw up that number, and it won't screw up that number, and I should be done. So how many oxygens are on the product side as written? 4 pairs makes 8. 5 singles makes another 5. 8 plus 5 equals 13. What doubled equals 13? It's not 6, and it's not 7, so I'll temporarily write 6.5. And that's good. And I'm done. 1 to 6.5 to 4 to 5. But evil science teachers like me say you can't have a half a molecule. So to keep this ratio the same and end up with only whole numbers, we'll just double everything. Therefore, the final answer is 2 to 13 to 8 to 10. And that is mastery level. To convince yourself that we're not just like wasting our time, this is what happens in your body every day. Molecules don't like have atoms disappearing and magically appearing. They're simply rearranging. And this is showing what's happening when we burn butane. Butane plus oxygen makes carbon dioxide and water. Notice the two butanes, C4H10 plus 3, 6, 9, 12, 13 paired up oxygens. They should simply rearrange to make these carbon dioxides and waters. If life is good, we'll get 8 of the CO2s and 2, 13, 8, and 10 of the oxygen of waters. And we do. 2, 4, 6, 8 CO2s and 2, 4, 6, 8, 10 water molecules. Chemical reactions are just rearrangements. They conserve mass. And we can divide up those chemical reactions into 5 basic types. Sometimes they just come together, like this. There's a name for that. We call that a synthesis reaction. That means combining. Other times they just do this. They fall apart. We got a name for that too. If it helps you to think of sad dating analogies, we're all adults here, feel free. That's breaking up, otherwise known as decomposition. Or they might burn. Look at this. We have something and we're combining it with O2, those two red atoms. C plus O2 makes CO2. Let's not just say burning. We could say rusting, iron to iron oxide. Best word is probably combustion here because I imagine you need a flame, but take your pick. Burning, rusting, oxidation, combustion, all the same thing. Here's another one. You're on the dance floor and you'd like to dance with that person in green. So what do? You say, may I cut in? And now you're dancing with green and yellow is not. But scientists don't call this like cutting in. They call this a switch, or better yet, a single replacement. Two couples on the dance floor decide to change partners. Like that. That would be a double replacement. So those are the 5 common types of reactions. Let's apply it to these things. A plus B makes C. Can you see how they're coming together? We call that a synthesis reaction. Here, it looks like this plus this makes that plus that. It kind of looks like a decomposition reaction. I said this plus this, but that was wrong. That's just one thing. One thing turns to 2, like this one was that one thing and it broke up. How about this one? Whenever you see O2 as a reactant, stop. Even if you think it's something else, it is by definition a combustion reaction, right? Now, if you think it's more appropriate to say rusting or something like that, please do. Like here, if you take iron and let it get rusty, turning into iron oxide, rarely do we do that with a flame. Normally, we just expose it to air. So I think I'd say oxidation for that one. That's a nuanced answer, not a big deal. If you get it, use the other one. Here we have 2 things plus 1 thing turned into 2 things one thing. That reminds me of something. Are we not switching out? That's a single replacement. And this one, AB plus CD makes AD plus BC, or something like that. That's a double switch, double replacement. Types of chemical reactions. Another specific type of chemical reaction is the acid-base reaction. We here on Earth live on a planet that is mostly water. We are mostly water, us humans. That being the case, acids and bases have everything to do with things that take place in water. For example, you could, in water, add something like hydrochloric acid with sodium hydroxide. And that is an acid reacting with a base. If it starts with H, it's probably an acid. Anything that contains H plus in it is an Arrhenius acid. Hydrogen chloride, hydrogen bromide, sulfuric acid, things like that. Anything that has OH minus is by definition an Arrhenius base. And when they combine, an acid plus a base makes salt plus water. Let's say that again. An acid plus a base makes a salt plus water. So when this combines with that, it's always plus minus, so we wouldn't combine H with Na, that would be plus plus. We'd combine the plus with the minus. That makes HOH. Wait a minute, HOH is water. And NaCl, we don't say ClNa, even though it looks this way. Always put the positive first. You don't say pass the chloride sodium. You say please pass the sodium chloride. So an acid and a base makes salt plus water. Now I've said it 3 times. The acid is H plus, a base is OH minus. So if you ever wondered what's an acid, what's a base, that's a good answer. Now, there's a few things that will make things more basic. That is, they'll raise the pH of water, but they don't have H plus. How can that be? This was looked at in the early 20th century, and they said, we better have a separate category for some substances that can raise the pH of water. If you throw ammonia, which is like Windex, for example, into water, the pH goes up, and that means that something's happening. And yet we're not adding hydroxide. It reacts to form hydroxide. It's almost like a secret base. You add it, and it makes hydroxide. Water plus ammonia will make ammonium hydroxide. So there's just a few that you need to watch out for. In this case, we're going to say that the water is acting as a Bronsted acid, and we'll check out the definitions, and this should all make sense. A Bronsted acid donates H+, and think of water as HOH, and can you not see that NH3 gained an H to form NH4? Therefore, it's acting as a Bronsted acid, an H+ donor. Bronsted base is simply an H+ acceptor, and when ammonia gloms onto that H+, it frees up OH-. Ha ha, a base. So ammonia is not in the strictest sense a base. It's something that makes a base, and therefore it's called a Bronsted base. Now, anytime you have something that is an acid and a base, you do have terms conjugate acids and conjugate bases. And you know what? I did not see it on the assignment. I didn't see it on the quiz, so I'm just going to skip it. You can look at those terms and try to learn from it if you want to go deeper, but I think you guys are sticking enough in your head as it stands, so let's stop right there. Let's move on to the next topic, which is pretty unrelated. It's gases. Remember how we started by saying things can exist as solids, liquids, or gases? This focuses on that one phase of matter known as gases. And if you're in the healthcare field, well, gases are essential to our survival, number one, right? Humans drop dead in a minute or two if they don't have oxygen present, or if the wrong gases are present. We need a lot of oxygen to go into our blood in order to survive. And if the pressure changes dramatically, that oxygen can get removed from our blood. That can happen if you go from 100 feet underwater up to sea level. The pressure can change by a factor of 3, and that can make the blood literally boil out of, I should say the oxygen will boil out of your blood. It precipitates, it hurts. It's actually happened to me. They call that the bends. So I'm just pointing out that gases matter a big time in the healthcare field. Maybe one of you is an I have trouble with that word. An anesthetist, right? Somebody who knocks people out. And that is all about the very, very, very careful use of gases to render people unconscious. Okay, but what we need to know about gases is their basic facts. Gases are substances that are devoid of intermolecular forces. That means they are so far away from each other that they're just like little dots. I like to think of that as a good thing because they're so easy to study if they're not interacting with each other. And we call that the kinetic molecular theory of gases. Think of it as what happens when you have dots far apart that don't interact with each other. That models gases very accurately. If that's true, then they're just tiny little points that have to have lots and lots of space in between. I believe there's a specific question about that. Gases are substances that are highly spaced from each other. And when they smack into each other, they seem to behave as if they're not slowing down. They just bounce off each other. I had a pool table when I was a kid, and I always think of that, only in 3 dimensions, right? They're not going to be attracted or repulsed by each other. They're not going to be gluey or stick to each other. They're just going to bounce around. They may hit each other, but that's an inelastic collision. They just bounce right off. They might hit a wall. They'll bounce off that too. But boy, that's really, really important because that when they hit that wall, they exert a force on it. That's what pressure is. If you got a lot of gases in here banging into the wall, a lot, high pressure, maybe enough to break the wall. And the hotter you get it, the more it'll bounce around. They'll increase their speed and it'll increase the pressure. That's the kinetic molecular theory of gases. Gases just bounce around. Now we'll try to relate 3 properties of gases. What happens when you heat them? What happens when you change the volume of them? What happens when you change the number of moles of them? So we'll mess around with pressure, volume, and temperature, P, V, and T. I don't think it's too complex because if you just had like a collapsible syringe, and you guys, a lot of you have worked with syringes, imagine a syringe full of air and seal it up and imagine what you can do with that barrel on it. That will really show you quickly how gases behave physically. That's what the study is. We're not turning gases into other gases. We're just imagining what happens if you take a syringe and push it in full of air. These are known as Boyle's law, Charles' law, Gay-Lussac's law, then 2 combined laws. One like this and one when you don't change the conditions, just what's in there. We call that the ideal gas law. Lots and lots of questions on this, both on the assignment and on the quiz. So we have to cover this covering 2 slides. This is our last topic. Hot gases will move faster, right? That's what will happen by virtue of kinetic molecular theory. And as such, gases have a very predictable behavior. They can be compressible. If you push in a syringe that's full of air, the volume will go down inside. Will it not? In fact, you can go from 50 mils down to 5 mLs. What's happening? The volume is going down and the pressure, you can feel it, is going up. So gases are compressible. What about when you heat them up? Take that syringe and take a blow dryer to the outside of it. You will see the barrel go up. They're expandable. As temperature increases, volume will increase, but only if it's an expandable system. And I like when they're expandable because it doesn't scare me. If they can't expand, if you heat up just a jar that's full of air or a tin can or anything else that has gases in it, we kind of think of it as being empty, but it's not. It's full of gases. Bad things can happen. They will pressurize, right? You take a round bottom flask, you seal it up with a rubber stopper, and then you put a flame underneath. Nothing scares me more. That thing is going to perhaps explode, right? That's known as Gay-Lussac's law. If you can't expand, it'll pressurize. So to summarize, as pressure goes up, let's do it this way. As the volume goes down, like pushing in a syringe, the pressure goes up. That's an inverse relationship. The initial pressure times the initial volume will equal to the new pressure times the new volume. Check out these words. 4 times 2 equals 8 times 1. First, do you agree? I do. 4 times 2 is 8. 8 times 1 is 8. And the 4 times 2 equals 8 times 1. The 4 turns into an 8. It doubles. It gets more. The 2 turns into a 1. It goes down by half. As one goes up, the other goes down. This is an inverse law. As temperature increases, volume will increase. That's a proportional law. As temperature increases, yikes, pressure will increase. That's a proportional law. We can squish them together and use this formula. And you don't have to memorize these. You can write these down, use them on a test. And they all iterate nicely in terms of this ideal gas law. I better spend a minute on this. The pressure of a system times its volume will always be equal to how much is in there in terms of the number of atoms. We call that moles. Times a fudge factor. We call it R, the gas constant. It's just a number to make it all work, times its temperature. Think of this as a picky law, however. Whenever you do problems like this, you have to use Latmok, liters, atmosphere, mole, and Kelvin for your volume, your number of moles, Your pressure, that's atmospheres, that's 1 atmosphere is sea level, times its temperature. And you gotta use Kelvin for your temperature for any of these because you don't want to go to negative numbers. Kelvin can't go to negative, but Fahrenheit and Celsius can, and that is messed up. All right, so I think that was a lot to throw in there quickly. I think when I do sample problems for the next two, I think you'll feel a little bit better. And that's what you need to do for the quiz and for the assignment, and solve problems. And here we go. If you had to memorize these things, it helps to know this little ditty. Boyle, the VP, saw Charles watch TV in Gay-Lussac's teepee. There he is, Sir Robert Boyle, watching Jacques Charles inside his little teepee. Why do we say that? Boyle's law is all about volume and pressure. Charles' law is all about temperature and volume, and the dangerous law is Gay-Lussac's law. That's about temperature and pressure. Let's solve a problem. What I recommend you do when you get these problems is save yourself some time. You could write down all your data. They almost always tell you to do that, but why write it down again? Just put, anytime you see a number, write a letter above it. I see 0.4, and that is liters. Liters is a measure of volume. I see a number 2, and they use the term atmospheres. Sea level pressure, what you feel probably right about now, is about 14.8 pounds per square inch of pressure of molecules hitting you. That's our initial pressure. And if it increases to 20 atmospheres, well, that must be a new pressure. We'll call that P2. And I don't see a number, but they do want a volume, so they want a V, so I'll just write V2 equals question mark. Then I look for the formula that fits, and I think it's P1V1 equals P2V2. By the way, you could just say if it goes from 2 to 20, wow, that's a tenfold increase in the pressure. I think the volume has to go 10 times lower from 0.4 to 0.04. So I just did it in my head. You can also write it down. P1V1 equals P2V2. There's your P1, there's your V1, there's your P2. Your V2 is X. I like to rearrange. You don't have to. But if we're going to take V2 equals, that means we'll take both sides and divide them by T2. Why? It isolates V2. Imagine P2 over P2. Well, that's like A over A. That's equal to 1. And we'll keep it on the other side. Oh, I didn't bother doing that. And maybe you don't want to either. But we'll just solve it that way. There it is. X is 0.04 liters, just like we estimated. Here's another one. Try to do it just like I said. You got a 2-liter balloon. What's that? That's our initial volume. It's warming from 25. Hey, so I guess temperature, right? So I guess T1's 25. Always use Kelvin. Add 273 to your Celsius. Otherwise, you're going to get impossible things. Negative numbers, when you double them, get larger. We don't want to be doing that. If you're warming something, we want it to get not more negative, but more positive. So always use Kelvin, and that's 298. It went up to 323. So instead of going 8 times plus, almost 9 times higher, now, is that right? 4, 8, 12. Instead of going almost 13 times higher, add 273 to this, and you'll see it's 596. And maybe you'll notice that it's simply doubling. The temperature is doubling. That means the volume should double. I think the answer is going to be 4 liters. But go ahead and set it up. Write down the formula. There it is. Plug in. That means replace numbers. Replace letters with numbers. For example, put a 2 for your V1, etc. And you got that. Now, to solve this, the best way is simply to crisscross. We call that cross multiplying. 298 times x equals 596 times 2. So 298 times x equals 598 times 2, but I don't want to, I just want to know what x is. So I'll divide both sides by 298. That isolates x, and x is just equal to those numbers. Practice doing that in case you said, what did he just say? It's called cross multiplying. Practice it a couple times. I'm sure I'll have to do another one here somewhere. So watch as I do it. And the answer is 4 liters, just like we guessed. The dangerous law. You got a fixed aluminum can, and it's got some air in it. It can handle a pressure of 4 atmospheres. I think that means that's the final conditions. Once it goes over 4, it will like explode. So I'm going to call that P2. And I got a closed 2-liter can. I guess that's my volume, but it's not going to change. It's a can. So that's one of those evil cases. It does happen sometimes where you got a number that you want to ignore. If it doesn't change, you can ignore it. But the initial pressure is at 1.2. That's a P1 for sure. I'm heating it from 25, so T1 is definitely going to be 25, right? No, add your 273 and get 298 and make it 100 higher. That's 373. So we got a P1, a P2, a T1, and a T2. And that's where your formula spits out. And that's the formula is Gay-Lussac's law. T1 over P1 equals T2 over P2. Replace those letters with numbers. Cross multiply. Watch me do it again. 298 times x equals 373 times 1.2. I wish I wrote it down in pieces because I did a step without showing you. I did 298 times x equals whatever this is, 373 times 1.2, but I want to get rid of the 298, so I divide both sides by 298. That's why this shows up on the bottom. I wish I could provide an example where I did that step out, but I hope you get it. Now we have a number, just punch that all in, and the answer is 1.50 atmospheres. Circle it and move on. No, read the question again. The question is yes or no, will it burst? Remember, it can go up to 4 atmospheres without bursting. It only went up to 1.5. The answer is no, it's not going to burst. So be sure to answer the question. Okay, 2 more problems and we are done with week 4. These are all ideal and combined gas law problems. So what I'd suggest you do is you could just, if they tell you what the formula is, just write PV equals nRT, and for this one write down the combined, and do the usual thing, replace your numbers with letters. But if you didn't know, you can do the same thing and see what formula spits out. 2 moles. Moles has a special letter, it's called N, so N is 2. The temperature we're solving for, we'll call it X. 300 millimeters of mercury. I don't think that happens in Rasmussen world. They'll only give you atmospheres to begin with. This problem was a little harder. I don't think you need to know it, but 760 millimeters of mercury is 1 atmosphere of pressure. So we have 307/60ths, or a little less than a half. We have 0.4 atmospheres. I think they'll just give you the atmospheres directly. And the volume is 12 liters. That is lat/mul, liters, atmosphere, mole, Kelvin. I like all those units. And they want to know the temperature. Hey, wait a minute. PV equals nRT, where's R? R is a given. It's always 0.081 liters atmosphere over mole Kelvin, so this time I do rearrange, I'm pretty sure. How do you just get temperature equals? After all, they're asking for temperature. Divide both sides by NR. NR over NR equals 1. Ha! It's gone. And we end up with PV over NR. Now we can take all 4 of those letters and just plug in those numbers. I like to do it with the units because I'm a careful person like that. Since that's exactly what R is, watch what the magic of the units do. An atmosphere divided an atmosphere is gone. A liter divided by a liter is gone. I don't see moles. Oh, look. Moles. Hey, isn't this moles squared? No, it's moles times 1 over moles. That's the same thing as moles over moles. That's gone. And here's another problem. I thought we were supposed to end up with a temperature in Kelvin, and this looks like 1 over Kelvin. Take a closer look. It's not. It's 1 over 1 over Kelvin. And the inverse of the inverse is the verse, which means it shows up on top. I kind of made that up, but that's what happens. And the final answer is 28 Kelvin. That's super cold. Last problem. Combined gas law. Now let's imagine we didn't even know it was combined. We'll write a bunch of letters here. 14 degrees Celsius. So what are you going to write? Hopefully you're an advanced student now and you'd say, T1 equals 287 because you always add 273 to get your Kelvin. I would say V1 is 4.5 liters. I would say T2 equals 302. And I'd say the pressure is doubled to 2 atmospheres. There's 2 pieces of information. The final pressure is clearly 2 atmospheres, but if it doubled, the initial pressure must be 1 atmosphere. I am just awash in T's and V's and P's. When you see like 5 or 6 units, it's got to be the combined gas law. It's the only one that has all those things. We're solving for the new volume. Wow. Write down the formula. I really don't recommend you rearrange it. I'm just obsessed with doing that. You'll have 5 of these 6 numbers. You'll have everything except that one right there. And you can just push your way through it and solve for V2. But I really like to isolate it so everything is neat and orderly. I'll divide both sides by P2 to get rid of P2 here. And I'll multiply both sides by T2 because T2 over T2 is 1. And by doing both of those, I will isolate V2, and there it is. Now I just got 5 numbers. I write them all in, and some units cancel. Atmospheres, atmospheres, that's gone. Kelvin, Kelvin, that's gone. Liters, I hope they're asking for volume. They are, the new volume. See the utility of including your units? And the final answer will be 2.37 liters. In summary, we have talked about matter. We've talked about solids, liquids, and gases. We've talked about phases. We've talked about phase changes. We've talked about balancing chemical equations, which shows up a lot on the test. We've talked about acids and bases, and we spent a lot of time talking about gases. This was a review of Week 4 Chemistry at Rasmussen College.